Now we can put that phase factor in, and we get that the irradiance of the reflection is, let's see, we had 4 times 0.04, that's 0.16 I naught. And I'm going to the cosine squared version. That's what the 0.04 is about, squared. And then delta, and it's actually delta over 2. I think in the previous board I forgot the 1/2 in the delta, so we'll stick it in later. So it's 2 pi over 2 delta path plus delta phase, like that, over lambda naught. Okay, so let's stick all that in. That's going to be equal to 0.16 I naught cosine squared pi. And then delta path is 2 pi in, or I'm sorry, 2t in. Delta phase is lambda naught over 2 over lambda naught. So we can keep going. It's equal to, when you get down to the end, 0.16 I naught cosine squared, and we can only simplify this so far. 2t in pi, I guess we'll distribute the pi, 2t in pi over lambda naught plus, and we'll just cancel, plus pi over 2. And that's probably far enough. This makes our point, IR, that the reflected irradiance that you get does depend on the wavelength, okay? And this is the reason for the colors. So we just did normal incidence, we haven't thought about angle yet, but just in terms of the wavelength, it shows up here. So as you change the wavelength, the cosine factor changes, and you get a different reflected intensity, okay? Also, it depends on the thickness. So the maximum color you might get will depend on the thickness and the wavelength, and the refractive index, etc. So what I've done now is I've plotted one of these where I've assumed, let's see, a thickness of 400 nanometers, so close to the optical, or a thickness of a film similar to the wavelength of the light. Index 1.515, that's glass, and normal incidence. And you can see that through the visible, from 400 to 700, it goes from essentially nothing, completely destructive interference, through a maximum here, sort of in the blue-green, constructive interference, to a minimum again, destructive in the red, yellow-red, and then it starts coming back up in the red. So you can imagine if you took white light and modulated it with this reflection, you would see colors. You would see something kind of green with a little bit of red mixed in, but mostly green. Okay. I can also show you what these interference effects look like in something that's pretty easy to make. So you take 2 microscope slides and you just stick them together, and they really want to stick together, lots of adhesion forces there, but they also leave a thin layer of air in between. So you may have done this before. If you just look at them and kind of get some light shining on them and kind of a dark background, you see these rings, these colorful rings. So here I'm going to show them to you. So we have our white light source, and I'm trying to show you some nice reflections, and there you can see the nice colorful rings right in the middle of the slide. It's sort of a ring structure in the middle because that's the shape of the air film. The glass comes into good contact in the center, and then it spreads out away from the center of the slide. So it makes sort of a circular shaped air film that changes with radius from the center of the slide. So that's due to a very thin film of air between the 2 slides. All right. So you have one slide here, you have one slide here, very thin film of air, and its width varies. So the thickness varies, thickness is also in the formula. So that's not exactly the geometry we calculated. Now you may ask, why do you have to do that? What about just the glass slide? And why is this section called thin film interference? Nothing about this required it to be thin, right? So let's try the same experiment with a single glass slide. So single microscope slide, very smooth, optically flat on both sides, and see if we can get anything. And here it is. And as you can see, perfectly smooth film, nothing really, no evidence of rings at all. So why? Well, the reason is it's too thick. It does require thin films. And the reason it requires thin films gets back to coherence. Whenever you have an interference effect, the two beams are split and they're brought back together. So the light has to be coherent over the distance, or you can think of it as the time, either way, that they're separated so that they come back together, their original coherence is still together. Right? So if the coherence length of the light is this long, then if we travel many times that length, then this section compared to this section, which is trying to combine with from earlier, are not coherent with each other. So you lose the interference effect. So the really thin air gap is thin enough that you get a coherent effect. The 1 millimeter thick slide is too thick to be coherent, or to cause interference, because it's too thick for the coherence of the light. And it's interesting, if you get into intermediate thickness things like a cover slip, sometimes you can hold it in one light source and see the fringes, in another light source and not see the fringes. And there you're measuring the difference in the coherence of the two light sources. So I used to teach this class. One year I taught it in a lecture hall that had incandescent lights over here, and it had some fluorescent lights over here above the board. So fluorescent lights are highly coherent, or well, are more coherent than incandescent lights. So I had this little piece of glass and I was looking at the fringes and admiring the fringes and how excited I was about them. And I handed them to the students to pass around the class and said, look at the fringes. Right? And they were all very nice and said, yes, we're enjoying these fringes. But somebody came in the end and said, actually, we didn't see anything. So I carried them over there, and the two light sources were different enough that I could see them here in my blackboard light, and they couldn't see it in the room. So if you get your hands on a microscope slide, a cover slip, the really thin cover slips, those are kind of fun to walk around and see when you can see the fringes. You'll see them in a fluorescent lamp, you won't see them outside, but you can give it a try.